Hello and welcome to this video about vector signal generation and demodulation for 5G and quantum computing applications. I'm Doug Jorgensen. I'll be narrating this presentation for you. Vector signal generation is something that MIQ Microwave has been working on, specifically MIQ Mixers, since shortly after the company was founded in 1991 by Ferenc and Christine Markey. Ferenc was already the world mixer expert, and he had a request for an MIQ mixer from a customer, and when the leading vendor of quad hybrids of the day wouldn't sell to him for some reason, he started designing his own. And that was the beginning of what has been a 20 or 30-year quest to optimize and improve MIQ mixers that make the heart of the vector modulators that we'll be talking about today. I will be your host. I'm the VP of Engineering at MIQ Microwave, and I've been thinking and writing about MIQ mixers for a long time. And this presentation was also put together by Duncan Pilgrim, our VP of Sales and Marketing, who has had an extensive career in RF and microwave components for a variety of applications. Now, to begin, I'd like to motivate your interest in this topic by discussing the capabilities that vector modulation brings to communication systems. If we imagine a basic digital communication system, an amplitude-only modulation where we have a 4-level signal, this provides 2 bits per symbol, and I'm plotting this on the constellation diagram that I'll explain on the next slide. Now, if we move to phase-only modulation, we can improve our resistance to noise by spacing apart our symbols, and we can increase the symbol density so we get 3 bits per symbol. But if we want to maximize the bandwidth that we have available, which is the quest of modern communications, then what we need to do is fit as much data, as many options as possible in the given bandwidth. And to do this, we use vector modulation, amplitude and phase at the same time. And we can get an improved signal density and an improved data rate without increasing the density of the constellation by going to vector modulation. But that's not enough. We need to cram more and more data in, so we go to denser and denser modulation formats. The cost of doing this, of going from amplitude-only modulation, phase-only modulation to vector modulation, is that these higher order modulation schemes, especially as you increase the density of the constellation, they're more susceptible to nonlinearity. So you need very linear components, you need a very linear system, and that's what a lot of modern communications has been focused on. Now, I've always had a hard time visualizing vector modulation, and so I'd like to present here 2 different ways that you can think about vector modulation that translate into 2 different ways of performing vector modulation. The first method to think about vector modulation, and the first method to perform vector modulation, is to imagine a fixed frequency wave. And you have to have a carrier frequency because this is RF and microwave engineering, and you always need a fixed carrier frequency for your transmitting information wirelessly. There's 2 salient features to this wave that you can modulate to get to transmit data. There's the amplitude of the signal, and there's the phase of the signal. And if you illustrate this, the state of the wave on Cartesian axes, you can visualize the amplitude of the wave as the length of a vector, and the phase of the wave as the angle of the vector, and hence vector modulation. This is also a convenient way to perform vector modulation. You can get an amplitude modulator, such as a variable gain amplifier or a variable attenuator, and you can get a discrete phase modulator, which can be built from a number of different technologies. And you can independently modulate the amplitude and the phase. And this is very commonly done for a number of applications, but most relevantly for beamformers for phased arrays. So for 5G phased arrays, they They sell beamformer chips, and what the beamformer chips do is they modulate the phase and amplitude of the signal going to each arm or each antenna in the phased array. And these are typically built in silicon. They're not ideal for direct modulation, though, because I believe that the amplitude and phase is too slow to switch using a phase modulator and a discrete amplitude modulator. The second way that you can think about the wave is, instead of imagining a single wave with an amplitude and a phase, you can deconstruct the wave into two constituent components, a cosine wave and a sine wave. And instead of either of these having a phase, they both just have amplitude. And you visualize this as an in-phase and a quadrature component of a single vector. So you can take the same vector and you can imagine it either as an amplitude and phase or as in-phase and quadrature. And they're equivalent methods of visualizing the state of a carrier wave. There are different ways of implementing it. So you can implement this I and Q modulation scheme. And the way that you do that is typically with an IQ mixer. And the benefits of an IQ mixer are that it's very fast. It's used for digital modulation. You can use digital or analog baseband data. And you can also, because it's a mixer, you can not just perform it from the baseband data, you can perform it from an IF. You can mix up from an IF using the same structure. Now, how does an IQ modulator work? Focusing on the functional aspects of the modulator. As I said, you take baseband data. This is data that's not on a carrier, and you input two amplitude signals. One is the I amplitude, and one is the in-phase amplitude, one is the quadrature amplitude. You can use digital data or you can use analog data, and you modulate a fixed frequency carrier. The output of this modulator is an arbitrary pulse or signal. So you take two amplitude signals and you get a phase modulated output signal. And this has applications, tremendous number of applications, obviously in communications. Also, they're important for radar and electronic warfare. They're used for quantum computing, and many more scientific, medical applications, imaging, radio astronomy, really any application where you use a high frequency wave, you can deconstruct that wave completely using an IQ modulator or an IQ demodulator. So what kind of do we care about when it comes to the performance of an IQ modulator? The first and most obvious is the amplitude and phase accuracy. So if you have a mismatch in the amplitude and phase accuracy, especially if you have a distortion, a nonlinearity in the amplitude and phase, then this will affect the error vector magnitude of your transmitted or received signal, and you may not meet the requirements of your communication system. The second concern is, in general, linearity. So advanced modulation formats like QAM, 1024 QAM, have high peak to average power ratios, and that leads to major amplitude excursions on the time domain of the signal. So I'm showing this two examples of this. As you try to filter harder, you actually get more deviations from the average. You get a worse peak to average power ratio, and you have to be concerned with linearity in every step, every component of your IQ modulator. So in the initial modulation, as well as in any conversions or amplifications, low noise amplifications, power amplification, switches, any other components in your lineup limiters, you have to maintain the linearity of the modulator throughout the transmission or reception system. The core of the IQ modulator, as you saw, that we are typically talking about, is an IQ mixer. And the IQ mixer has a fairly simple structure. It's two identical mixers. The mixers are the core that provides the mixing performance. And they're combined together with an LO quad hybrid. LO quad hybrid is really the magic of the IQ mixer. The phase of the outputs, how close the phase of the outputs is the key metric for performance for an IQ mixer typically. And then there's an in-phase splitter or combiner. And this is so that the IF, the I and the Q are low frequency, the LO quad hybrid and the in-phase power divider for the RF are typically at the same frequency, and that's the high frequency portion of the IQ mixer. You can use the IQ mixer in 4 different ways. 2 as an actual modulator. So if you're trying to create a vector modulated signal, there's the way that you can do it that is sort of the obvious way, and then there's the high performance way to do it. And these map onto different ways of using the IQ mixer. So you can use the IQ mixer as a direct modulator. This is where you have baseband data and a carrier frequency, and you just modulate the I and the Q with the baseband data, like I was explaining before. And this is subject to all the way that the distortions of the mixer manifest themselves are in terms of amplitude and phase balance and L to R isolation, because your LO is right in the middle of your signal, and the LO by 1, 2, 3, 4 IF spurs are all inside your signal as well. The analog, the carrier analog to that, if you have your baseband data and you put it onto a carrier, then you can create 0 and 90-degree versions of that and feed it in. That creates a single sideband up converter. In the case of the single sideband up converter, you have the same distortions, but the balance that distorts your constellation in the vector signal modulation is what causes imperfect sideband suppression. Imperfect balance means imperfect sideband suppression. You still have the L to R isolation to worry about because the LO bleed through is right in the middle of your signal, and you still have the spurs to worry about, depending on how high your IF frequency is. The down converting analog of vector signal modulation is vector signal demodulation. This is also sometimes called 0 IF demodulation. And this is where your LO and your carrier frequency are the same, and you demodulate directly to baseband. And if you have imperfect balance in this system, then your I and your Q data will overlap each other. You'll get I data in your Q path and Q data in your I path. You also get some odd distortions. The L to R isolation manifests itself as a DC offset, which is also a characteristic of phase detectors. When you use an IQ mixer as a phase detector, it's problematic. And then you also have second order, even order distortion. 0 IF demodulation has a lot of different issues that if you search for 0 IF demodulation, you can find many papers on the techniques that you can use to overcome these limitations. And then there's the analog to this with a carrier IF, or the down converting version of a single sideband up conversion, is an image reject down conversion. And this is very commonly used to eliminate noise in a wideband receiver. So if you're trying to get the lower sideband, then you would take the in-phase components, for example, and the noise at the image frequency is rejected. This is commonly used because you don't have to worry about DC offset or LO to RF isolation. The balance is manifest as image rejection, so you do have to worry about that, and you do have to worry about M by M spurs, so 2 IF, 3 IF, etc. But it's a very commonly used technique for high performance 5G signal analysis receivers. So I'd like to show, give some numbers, I guess, or give some more intuition to the performance metrics of the IQ mixers. So the headline spec is always the IQ balance, and if you're looking at the spectrum of an upconverted signal, you'll see the desired signal, the desired sideband, and this is pressed sideband. Typically, an easy to hit target for sideband suppression is like 15 dBm. You can see that you don't need that good of phase and amplitude balance. And the target that we hear a lot is 70 dBc with calibration. And that's so the 70 dBc is even better than 70 dB. So sideband suppression should be in dBc. I should be giving this number in dBc. LO to RF isolation is usually in dB. And the difference is whether you're measuring relative to the carrier or relative to the input. So relative to the carrier is a much higher bar. So 70 dBc is a very crazy number. You can get it with calibration if you're, I understand that you can get it for brief periods with calibration if you're very careful. Our mixers, our IQ mixers, typically have numbers in the 25 to 40 dB range, depending on the frequency that you're at. And that's very, very good across broad bandwidths. You can see that you can see the difficulty of maintaining that. You need around a degree of phase error and around what 0.25 dB or less amplitude error. The phase error comes from the LO hybrid. I'm going to talk about different ways to make LO hybrids, and there's some amplitude and phase error due to the non-ideality of the mixers and power dividers. This has helped tremendously if you use a MIQ mixer, because the MIQ mixer has identical copies of the double balanced mixer and very consistent. It comes down to manufacturing tolerances. So however you build the product, if it has better manufacturing tolerances, then you'll get better ideality in the balance of the mixers and power divider. The LO to RF isolation, this is limited by the mixer cores. And you can see that shows up right in the middle of your desired sideband, your desired spectrum if you're upconverting. And I mentioned the linearity. It's determined by the mixer core primarily. And it manifests itself as IP3, spectral regrowth, P1dB, and multitone spurious. And you can do a little bit better than mixer core linearity because you're doing some power splitting, so you get a 3 dB improvement. You also get some spur improvements, but typically they don't actually help you in your system. They're for spurs that you don't care about usually. Okay, so what mixers? So I talk about how great our Marquis MIQ mixers are. You can see that the bandwidth ratios on the mixers that we have are as high as 9:1 with the MIQ 0218. For a planar structure IQ mixer, this is really record-setting, state-of-the-art industry stuff. We have a wide variety of MIQ mixers, MIQ IQ mixers, stretching up to 67 gigahertz. In surface mount, like I said, the image rejection, the typical image rejection is around 27 to 35, 25 to 40 if you at a given frequency, and the L to R isolations are really exceptional on our MIQ mixers, up to 60 dB, typical numbers. Broad frequency coverage of all the typical 5G bands, C band, S band, and we also offer unique diode options, so H and L diodes for most of our mixers. We even offer an S for the 1867, which is a super high barrier. So if you have more LO drive, and remember it takes more LO drive for an IQ mixer, you can get even higher IP3, you can get higher P1dB. Similarly, for die and modules, we have the same products that we have in surface mount, plus we have an IQ mixer that goes to 90 gigahertz. Similar performance specs, 90 gigahertz in die form. We have the MIQ 4067, which is the 4090 in a package, and we're working on pushing this to, higher frequencies. The LO drive is a little bit better in the on the bare die module than it is in the surface mount, as low as 3 dBm, and high IP3 to 27 dBm. So I'm going to talk a little bit more about the core components that go into an IQ mixer. There's the quad splitter. This is single tone only. The phase balance is the most important thing. Amp balance is less important because it's just a switching signal. For a vector modulator, if you're using it as a vector modulator, the amplitude balance becomes more important depending on the exact power levels you have between the I, the Q, and the LO. The power splitter on the other side is an in-phase power splitter. It can be reactive or it can be resistive. Wilkinson combiner is what we find to be the best in our experience. The phase and amp balance is critical, but it's usually pretty not easily achieved, but it's not as difficult to achieve as is with a quad splitter, for example. And then there's the mixer core. These are typically almost identical to our double balanced mixer cores, our MM1 mixer cores, and these determine the isolations and linearity of the MMIQ or the IQ mixer device. Now I'm going to talk about some different ways to implement quad splitters that we don't implement most of these, but if you were trying to build your own IQ mixer, these are different ways that you can use to implement your own quad splitter. So there's the power divider with delay line. This is the most obvious way to do it. You just take if you have a single frequency, you take a power divider in phase, you add a 90-degree phase shift or time shift to one side, and it's easy to implement. You can tune it. You can get very, very good phase balance depending on how tightly you can tune it, but it's single frequency. Also, you don't have good amp balance typically. Next is a branch line coupler. This is a very basic circuit that you can design in microstrip, and it is easy to design. It's pretty easy to build. Low loss and planar. It has isolation. It has an isolation port, which always makes things perform better. But it's fairly narrow band. That's why we don't use them. They're physically large as well. Another reason not to use them. The third one is the polyphase filter. This is the most common 90-degree phase shifter in the world. From a circuit standpoint, it doesn't have very much going for it. It's high loss. It requires a differential input and output. The power handling is low. The isolation is poor. There's not much to recommend it, but it is cheap and small and integrates on CMOS, unlike all of these other circuits which require full planar microwave circuits. So the polyphase filter, very common. Now, some of these are ones that we actually implement. The Lang coupler is very, very commonly used for IQ mixers. It's pretty wide band. It's almost planar if you've got this crossover. You can integrate it. It has a lot of features. It's not too difficult to design. So we use these on our high frequency IQ mixers because you don't need as much bandwidth on higher frequency units. The T flip-flop, this is the way we've always thought would be cool to implement a quadrature split. Digitally you create a 2F signal, and then you use flip-flops to output, basically to cut the signal in half, and then you have a 0 and 90-degree signal that are limited in balance. They're theoretically perfect. They're limited in balance by the jitter of the clocking system. We always thought it would be neat to implement an IQ mixer this way, but we haven't done it yet. The way that we implement many of our IQ mixers, including the MMIQ 0218, is using the 3dB quadrature coupler. This is the best 3dB coupler. This is the best 90-degree phase splitter you can create in terms of bandwidth. The loss is good. The balance is excellent. The phase balance is nearly ideal across super broad bandwidths, and it has high power handling. The cons are that it's large and difficult to make planar, and these are all problems that we have solved for our customers, so we recommend that you just buy them from us. I'm going to talk about, I mentioned earlier that you could get up to 70 dB of up to 70 dBc of spur rejection or amplitude rejection of your sidebands and LO. And the way that you do that is using calibration. Almost all users of IQ mixers perform a calibration on them. And the procedure is pretty well known. First, you null the L to R feed through in the core mixers by introducing a DC offset. That's what these bias tees are for. They introduce a DC offset. Next, you adjust the phase of the I and the Q ports on the IF to achieve maximum suppression. And this is basically you're just matching the LO hybrid. So if the LO quad hybrid has a loss of 5 degrees, or an imbalance of 5 degrees, then you set the quadrature balance to -5 degrees. And it really is that, it really should work that simply. What makes this difficult is that you have to repeat this for every LO frequency and every temperature that you're going to use it, because the phase walks across those parameters. You also can adjust the amplitude of the I and Q signals, assuming that you're using a DAC or an ADC as your transmitter or receiver at an IF. So this is the way that people almost always use mixers like this. That's the reason that they have to be double balanced, is so that they have a DC IF. You can tune these things. How much improvement you see depends a lot on the calibration system that you use, but it always helps to start off with a well-balanced mixer to start. The walk will be much less if you have a tightly confined, well-balanced mixer. And this is a technique that's very, very commonly used by quantum computing customers. So I'm showing the application of MIQ mixers as vector converters for quantum computing. In this case, the IF is generated, the I and the Q are generated by a DAC or read in by an ADC, and they feed the IQ mixer. To go back, the whole application for quantum computing is basically you create a quantum well using an LC resonator at very, very, very cold temperatures using a nonlinear inductor. So that's what Josephson junction is, a nonlinear inductor. And the qubit states are 0 and 1 are the lowest qubit states in the well. You couple together multiple qubits, you cohere them together, and then you create these readout pulses and control pulses. So you set them all to a specific state, and then you modulate the state, you entangle them together, and then you use a readout pulse to generate the output. So this is an application where you have an analog input signal, and what you're trying to do really is get complete control over the vector signal, the phase and the amplitude of your pulse. Now, the best way to design using our IQ mixers for these complex applications is with our nonlinear device models. So as parameters are not meaningful for nonlinear devices, they don't capture, they're intrinsically small signal devices. So Markey offers nonlinear simulation design kits for Microwave Office and for ADS. And these are the actual designs of our nonlinear devices. So we're not creating behavioral models by measuring the device after we create it. This is what we have designed to, and it just uses our nonlinear device models, like our transistor and diode models, combined with the 3D models of the circuitry around it. So to that extent, they're about as perfect as you can get for physics-based models, and they also capture a tremendous amount of capability, because we're not modeling, we aren't saying this is a mixer and then giving it mixer parameters. All we're doing is creating a 3D electromagnetic structure with diodes or with transistors in it. And it doesn't know that it's a mixer or an amplifier or a doubler. It just calculates the currents and the voltages across the transistor or the diode. So it's very powerful and can perform a wide variety of simulations that otherwise may not be possible. Our latest release supports over 100 parts, including 16 MIQ mixers, and we try to update it on a quarterly schedule with all of our newest products. So I want to show you the power of the simulations that we can do. First, there's the basic simulation. So this is what we do when we're designing it. We try to optimize the image rejection, the L to RF isolation, and the conversion loss in simulation. And then we produce the part, and this is how it compares. The conversion loss is very well modeled, looks nearly identical. The L to R isolation is typically overestimated in the simulation. You'll never get as good of L to R isolation in reality as you do in the simulation. So you always, the reason for this is that it's so well balanced that any, when you're talking about 60 dB of isolation, any fluctuation in the amplitude balance of the balun or the phase balance will lead to degradation very quickly. We do better on the down conversion, or the image rejection, sorry, the image rejection of the sideband suppression, because it's just not as strong a vector cancellation. So, we don't hit the exact humps, but you get the envelope of the performance, usually pretty close. Now, I said that this is a physical model. It's not a behavioral model, and that means that you can do non-standard simulations, like using it as a basic vector modulator. So you can plug up a current source to the I and the Q and see what the insertion loss looks like. And indeed, the insertion loss doesn't look like the conversion loss. It includes the loss of the quad hybrid. And you can see that the insertion loss versus phase, a little more complex parameter, has the same average value. It's got some more noise on it. So different types of simulations can come out closer or farther away. And so you have to be careful how you use the simulator. But we wanted to see if we could use the basic mixer model with no modification to do a direct vector modulation simulation. So the vector modulator to create the vector modulator, we create a 2-level voltage signal, and then we filter it with a low-pass filter, a data filter. And then we use this impedance matcher to match our voltage source to our I and our Q ports on our mixer. And you can see that indeed this basic 2-level signal into each port of the mixer generates a 4-level QAM, 16 gigahertz QAM, QAM 16. And this is at 28 gigahertz carrier frequency, but this is only a 24 kilohertz carrier rate, data rate. Not very interesting. So we bumped it up to 100 megahertz to see if it could handle that. The mixer should be able to handle 100 megahertz very easily, and it does. You can see that the constellation is rotated because of the way that it's plotted, the way that it's received. We never figured out exactly why, but the constellation still looks good. And then we try to push it up to real 5G data rates, 1.3 gigahertz of bandwidth. And here the mixer is still doing okay, but the simulator starts to have problems because the simulation step size of the data rate starts to approach a fraction of the carrier, and so that creates problems for the simulator. But the mixer itself still works okay, and with some more work, I think you could figure out how to get the simulation settings right to get a good constellation. And then one more simulation we wanted to show, where instead of using the mixer as a baseband modulator, we created an IF frequency. And so we're using this ideal IQ modulator with the I and Q components to create a 64 QAM, and then we do some conversions to it, create an IQ version of it, and plug that into the mixer. And this is a single sideband up conversion instead of a single sideband up conversion instead of a baseband modulation. And you can see that the simulator still has no problem simulating it because it's a physics-based model that can handle all of the transients necessary to show the output constellation. We only did this up to a 1 megahertz baseband, however, because once you have multiple frequencies to keep track of, the simulation time starts to bog down. So, key takeaways from this talk: vector modulators enable many important applications because you have complete control over the signal. There's only two components to a signal, and you can control both of them using a vector modulator. This is important for 5G communications. It's important for quantum computing. It's important for radar, almost every other application. IQ mixers are ideally suited to build high-speed vector modulators, and the critical performance parameters for IQ mixers are balance, isolation, and linearity. This is what we focus on when we're designing our IQ mixers that operate up to 67 gigahertz in surface mount and 90 gigahertz in bare die. And all of our mixers have associated nonlinear models, which allow you to perform complex application-specific simulations that you may not be able to perform using alternative models. I'd like to thank Andy Howard, the extraordinary applications engineer from Keysight, as well as Andrew Chong for providing us the demo licenses of these various simulation tools, simulation engines that we usually would not use. Usually we just do harmonic balance simulations to demonstrate, to design our products. I'd like to thank Ryan Bunk from Markey for doing all of the ADS simulations. And thank you for your attention. Have a great day.